Thank you, and thank everybody for being here, and thank you, AMSE, for inviting me to give this presentation. So this is joint work with Hanwei Wang at City University Hong Kong, and it is going to exploit Chinese data. So Hanwei would be the co-author that can answer all questions on the Chinese data. I can answer only a subset of questions on the Chinese data. So in this paper, what we do is we go back to this old concept of revealed comparative advantage, and we try to see whether we can come up with new measures that are exploiting micro and macro data. So what is this idea of revealed comparative advantage? So first of all, I mean, it is about retrieving some of the basic fundamental parameters of trade models, and in particular, in our case, would be the Ricardian trade model. So what are these basic parameters? So here is a quote from Bernhofen and Brown. So the famous 4 numbers paragraph for comparative advantage by Ricardo is one of the oldest analytical results in economics. And what is this about is essentially the labor content of production. It is an important, these are 4 important or magic numbers because interpreted as unit labor requirements. These numbers have provided the basis of Ricardian model of international trade from the beginning up to recent years. And this recent paper, well, recent, 20 years ago, by Eaton and Kortum, has affected the entire literature in quantitative trade models afterwards. The 4 numbers refer to the units of labor required to produce a unit of output in 2 industries that are active in 2 countries. So, of course, those in international trade, they've seen that so many times. But I want everybody to be on the same page because this is what we are going to measure. This is what we are after. And so a country has a Ricardian comparative advantage in an industry if in that industry the unit labor requirement is relative to the other industry is lower than in the other country. So this is the basic idea of comparative advantage. And in the traditional Ricardian model, these unit labor requirements that are essentially the inverse of total factor productivity are exogenous determinants. So these are exogenous numbers. And the prediction of these models is straightforward, is that a country is going to export the product in the industry in which it has a comparative advantage and import the other product. Now, revealed comparative advantage comes in. And so these numbers are very, I mean, the 4 magic numbers are very difficult to get hold of. And the point by Balassa, again, in his old paper, is that if you want to understand where the comparative advantage of a country lies, you can essentially use this implication and work back the comparative advantage, meaning that the endogenous trade patterns reveal the exogenous Ricardian comparative advantage. So if a country is exporting in the sector in which it has comparative advantage, then you can look at the export and say, okay, this is the country is going to have a comparative advantage in the sectors in which it exports disproportionately. So you look at the specialization in exports with respect to the rest of the world, and you can assess what is comparative advantage. The Balassa index, or revealed comparative advantage, is therefore based on the degree of a country export specialization, and it is considered to be a sufficient statistic for identifying the existence and magnitude of Ricardian comparative advantage. Now, all this works through quite beautifully if you have exogenous labor requirements and if you have clearly only Ricardian model in mind. This is problematic when you look at real-world data because there are 2 problems with this revelation principle. There are many problems, but the 2 that I want to highlight and address in this presentation. The first is that maybe labor is not the only input in production, and so there are other inputs in productions, and relative factor intensities varies across sectors, and so we are entering what is called the echelon world. And so comparative advantage in terms of opportunity cost may not align with the Ricardian comparative advantage in terms of technology or relative unit input requirements. And this is something that was already pretty clear to Balassa, but also in recent works on comparative advantage has been highlighted. Another important aspect is that with imperfect competition and firm heterogeneity, there is endogenous selection of firms that survive. And so what you observe in the data is determined by the TFP, or the technology of the firms that survive, and not necessarily this is determined by the underlying comparative advantage of the country. So with perfect competition and firm heterogeneity, well, there is a distinction between exogenous comparative advantage and endogenous comparative advantage. Exogenous would be the country's characteristics in terms of technology, and endogenous is the outcome of selection. And selection is affected by many things, including the degree of openness of countries. So in this sense, when you try to get to the data, this Balassa index or revealed comparative advantage is not a sufficient statistic for Ricardian comparative advantage, because there are so many things that are going on and are affecting the pattern of trade. So what we do in this paper, we try to answer these questions. Can we find sufficient statistics for Ricardian comparative advantage when we consider both the Ricardian aspects and the echelonic aspects in a situation in which we have a selection of firms, so endogenous selection? And then once we have the sufficient statistics, we say, okay, if one is interested in Ricardian comparative advantage, which data are needed to implement these sufficient statistics? And possible, I mean, just to make it a little bit concrete, one may think that now that we're seeing a convergence in factor prices, especially in the cost of labor in China, we expect to more advanced economies. What should we expect in terms of sectors that would become competitive in the Ricardian sense as this convergence takes place? So where is the actual Ricardian comparative advantage of China? In which sectors? And then what is embodied in the, so once you have these sufficient statistics, they can tell you they are not, as we just argued, they are not the revealed comparative advantage of Balassa. One may also ask, but then what is this Balassa index actually revealing? So what is revealed comparative advantage actually revealing when we have all these complications in mind? So the contribution is we try to cut new ground in terms of sufficient statistics for Ricardian comparative advantage, and we do that through a quantitative trade model that has all these features. And in terms of the empirical application, we show that the model's micro foundation are important, but not because you necessarily need microdata in order to compute the sufficient statistics, but because you need the microstructure of the model if you want to understand which macro data you can use. So without the model, you would not know which macro data you need to use. In the application, we use Chinese firm level data for the micro foundations and also for motivating some aspects of the model. And then we use cross-country sector level data to compute the sufficient statistics based, sorry, there is a typo here, based on macro data. We compare the ranking based on revealed comparative advantage with one based on the sufficient statistics to see what is the difference between the two. And then we go back to this sort of example question that is, we discuss which Chinese sector may gain prominence in exports thanks to the emergence of Ricardian comparative advantage when the labor cost advantage disappears. The literature, of course, on comparative advantage is huge, and I'm here highlighting only some aspects. So what is relevant for us is clearly models of comparative advantage with heterogeneous firms. There are not that many. A lot of papers are instead on the macro implications of firm heterogeneity. Since Eaton and Kortum, a lot of papers have used generally inversion of the quantitative models in order to measure comparative advantage. And then, I mean, since in the data we have this issue of multi-product exporters that are very important, we also contributing to this literature. So something that I want to clarify immediately is with respect to what we have here, the measure of comparative advantage. So just to intuitively, what the models of comparative advantage do is essentially they take this unit input requirement, then they build all this structure and they get implications for the observables. And if you believe in the model, you can take the implications for the observable and invert the model and back up the underlying unit input requirements. In order to do that, you have to solve the entire model and invert the entire model. The approach that we use here is instead sufficient statistics, which means that you don't have to invert the entire model. If you realize that what you're after, this unit input requirement, are related only to a very small subset of the endogenous outcomes of the observables. And so it is essentially something that can give you, it's much easier to apply because you don't need to do any sort of mathematical computation and inversion. So stylized facts to motivate the analysis and particularly some aspects of the model. Then I will present the theory and then I will get into the quantification. So the data are Chinese data from on industries and trade statistics. There is, of course, a matching process, and there is a computation of firm TFP that is based according to recent state-of-the-art methods. There are some aspects that are not entirely satisfying in terms of these methods for what we do. But for those who are interested, you can ask questions, otherwise it becomes too technical. Why we want to have these firm level measures of TFP? Because remember, there is this issue that you have some country characteristics that are determining the endogenous selection of firms, and therefore what you observe is essentially the outcome of selection, and the outcome of selection is, the composition of all these firm level TFP's levels. At the industry level, we measure TFP as an average, and industry labor intensity, because we want to have this X-shareholding component, by average labor shares across firms in 4-digit industries. And the labor shares are measured by labor cost divided by value added, so it's how much the wage bill over the value added of firms. And the labor cost for us include wages, insurance fees, employees' benefits. And the entire analysis made with, as a baseline 2004. Why? Because in 2006, the Chinese data were some way updated and some parts of the dataset was discontinued. So after 2006, we would have problems in computing some of this stuff. Motivating evidence. First, stylized fact. Export propensity and intensity rise with labor intensity and productivity. So what is export intensity? What is labor exporting propensity and intensity? So export propensity is the fraction of firms in an industry that are exporters. Intensity is instead, in the industry, the ratio of exports to production, to output, or to sales, to be precise. So essentially, it is export per firm. This is the fraction of exporters in the industry. So these are the two panels. What you have on the axis, you have TFP in the different industries, increasing from left to right. And you have labor intensity in the industry increasing from bottom to top. And then you have this plane that is measuring export propensity, and the dots are the different industries. And what you see is indeed that export propensity increases with labor intensity and increases with TFP. So in sectors that are more productive, which firms on average are more productive, and sectors that are more labor intensive, you have more exports. Sorry, for China. And this is a good question because this aspect here is some way consistent with some intuitive idea that China in 2004 was labor abundant with respect to the rest of the world. Export intensity is, again, the same picture, but now we have the exports per firm on the vertical axis. And so you see that also export intensity is increasing in the same way. So to simplify things, one may think that this is showing both Ricardian and Echelon forces at work, because you have that if you believe that China in 2004 was had an advantage in terms of low labor costs, then this would be the Echelon implication, and the other one is the Ricardian implication. So second stylized fact. Now we get into the firm's data set. Firms' export product scope rises with industry labor intensity and productivity. And so here, what is the export product scope is the number of products exported by a firm on average in an industry. And so it is, we could have plotted the same type of information in a graph like the previous one. It would have shown that indeed, once more, in sectors in which firms are on average more productive and they are on average more labor intensive, you have, in this case, a larger number of products exported. So it is easier to export in these sectors, also at the micro level within firms. And then the third and final fact is that the skewness of export product mix falls with industry labor intensity and productivity. So you plot the same type of picture, and what you see is that not only it is easier to export for a firm because you export more products, but also you have that the composition of your product bundle is going to change with labor intensity and productivity. That is in sectors that are labor intensive and high productivity, you have that your export product mix, so the distribution of your sales across products is more balanced. Now, these are three things that we needed to motivate, or to make some to motivate the assumptions that we're going to make in the theoretical model. So let's see how we can get to that. Intuitively, what we want to have here is essentially Echelon and Ricardian forces for the first stylized facts. For the second stylized fact, we need to have some idea that in sectors in which you are competitive, it is easier to sell a lot of products for the firms. And this one is the trickiest one, because here, despite the fact that it is easier in this sector to export a lot of products, you also have an effect on the product mix. That is, having this more balanced distribution of sales across products means that your products are equally or similarly competitive. But since our products are better than others, if you have this balanced distribution, it must be that the competition you face abroad is not that tough. Because otherwise, if competition were tough, you would sell a lot more of your best products than of the other products. This has something to do with the shape of demand, and I will discuss this. But in a sense, it's sort of a Champions League model of trade. If you are facing a competitor in your national league that is not, football league that is not that challenging, you're going to field all the players, rotate all the players. If instead you have to play the Champions League with very tough competitors, you field only your best players every time. And this is something that you see in the data for products that when you look at the level of firms. Yes?
Could you tell me exactly to what it refers, FLI index?
Yes. Sorry, I didn't get into the details. So how do we measure the concentration of the product mix? So you have this distribution of sales across products. So you could take any moment within the firm. So the first statistic is the simplest one, because most firms, they sell one product or two products. So if you want to have a large number of firms, you're going to look at the ratio of the sales of the first product to the second product. And the larger is the ratio, the more concentrated is your product mix. But then I may say, okay, you have all these indices in IO of concentration, and so why don't you use also something that is taking into account a larger number of products? And so this is the Hirschman index. It is across products for the same firm. So this is what is this saying. So essentially, the idea is that the larger is the ratio of the first to the second products, well, the larger is industry labor intensive industry TFP. This is an inverse measure of telling you essentially the same thing. So in the theory, much of this is fairly standard, except I want to spend some time on the utility, because this is going to play a role also in terms of the quantification. So this is, in a sense, a standard MEDIS model on international trade. What is a standard MEDIS model on international trade? You have, in our case, 2 countries, home and foreign. Foreign variables are labeled by a star. There is a continuum of industries, index Z from 0 to 1. The structure is pretty in line with very old papers by Dorbush, Fisher, and Samuelson, who were looking at these 2 countries set up with a lot of sectors. And the utility is this animal that looks strange, but it is not that strange. So first of all, I mean, there is a log here and the B in front. So there is an upper tier utility that is Cobb-Douglas. Because then, of course, you can bring the B up here. Inside this top utility, there are sub-utilities that are defined over sets of available varieties of different products. So there is a product Z in each industry. In each industry Z, the set of products is omega, and I is the index of the product, so it's a product in this industry. And then what you see here are 2 components. There is a component that is the integral across all these varieties, but essentially you can think that as a sum, so it is the total sum of consumption, which means that for this component, it doesn't matter how you allocate your consumption across varieties, because it's just the total amount of consumption that matters. But there is a second component, and the second component is introducing a penalty for concentration of consumption of a few varieties. And so again, as Tanguy was asking you before, if you think, for example, this as a delta equal to -1, this would be a 2. And so this is a sum of the squares, looks pretty much like another Erfindel index. And so this is an Erfindel index of concentration with the minus in front. So there is a penalty if you focus your consumption on a subset of varieties. So it is what is capturing love of variety. You like to consume a lot of varieties, or product differentiation. You want to consume different varieties because you perceive them as quite different. Now, this type of utility will deliver a demand system, which is named after people that work on that again years ago, a Buelow-Fehlers type of demand system that has some interesting characteristics that we will see. But before getting to there, just the interpretation of parameters, alpha is telling you how much you like consumption, no matter how composed of the varieties, and gamma is telling you how much instead you're penalized if you concentrate consumption on a subset of varieties. So essentially the ratio of gamma to alpha is going to tell you how much you love variety. This thing here, if you forget about everything else, is just a CS demand system with constant elasticity of substitution, which is what in quantitative trade models is always used. And so this, in a sense, given the inertia in the profession, this is the thing you have always to discuss. People use this because it is easy. I will try to show you that the rest is not that complicated. But keep that in mind, because we will always have the possibility of understanding what difference there is between a simple CS system and this more complicated system. okay? If you have the maximization of this utility with respect to the budget constraint, you're going to get what I said is called a Bülow-Lederer type of demand curve, because you have that the price is equal to some constant here, which is not constant in our setup, but say some intercept, minus this term here, so it is negatively sloped, and we have to, before getting confused in the use of this demand, we have to clarify when we get a linear demand, when we get a CS demand, and when we have a combination of the two. So if delta is equal to -1, and gamma is larger than 0, so this is a downward sloping linear demand. If alpha is equal to 0, and delta, therefore P max is equal to 0, and delta is larger than, is positive and gamma is negative, we have a CS demand. What we will use is so why is that important? Because it's telling you that by changing the values of the parameters, you can play with this demand function. And you can make it as CS as you like or as linear as you like. And this fact that this demand is a mixture of other demands that are used is transmitted to all the results. So for example, the elasticity of demand or the elasticity of substitution has two components, the CS component, which is a constant, and then it has the linear component, which is the part that is telling you that the elasticity is going to be affected by the prices of the firm and by this P max. So what is the P max? This P max is the maximum price that is feasible in this market, and it is endogenous determined by the selection of firms. And so this is a demand system that is telling you that if your firm is pricing close to this maximum price, so the choke price for demand, then elasticity will be very large. If it is priced away from this Pmax, then it's going to be very low. So you see it's a combination of these two. It's this top of these two demands. On the production side, there is a multi-product production, but essentially it's just a simple variation of the standard merits model. So when firms want to produce, they have to pay a sunk cost of entry. If they pay the sunk cost of entry, for sure they are able to produce something, but ex ante they don't know how good they will be in producing. So they're going to discover how good they are in producing only after paying the sunk cost, because after paying the sunk cost, they're going to draw their productivity, or the inverse, which is the unit input requirement, from some distribution. So after they enter, they discover how good they are and decide whether they want to produce or not. They can also decide to produce more than one product. And this is done through a flexible manufacturing type of technology. You draw the unit input requirement for your core product, so the thing that you can do the best, and then you can create other products by customizing or the original product. And this comes as a cost, which is increasing with the distance from the core product. So here you have the marginal cost of production for a firm that has drawn a unit input requirement C upon entry and is considering producing a product that is M steps away from the core. So what is the marginal cost of production for this product is going to be the unit input requirement for the core product amplified by a term that is increasing in M. So this parameter is between 0 and 1, and therefore the power of minus something positive is going to be, or larger than 1, is going to be larger than 1. So you can move away from your core product, but you are becoming less and less efficient, which means that given this demand, sorry, where is it? Now I'm going backwards. Given this type of demand, with a choke price, at some point you will not be able to sell additional products because they are too expensive to sell, and therefore you cannot stay below the Pmax. Now, a firm that has a marginal cost V, sorry, not a marginal cost V, this is the unit input requirement V for a given product, in order to produce has also to pay the factor price. And so this omega Z is the price index of the factor bundle that the firm is using. So we were saying ex-shareholding would have capital and labor. This is capturing the combination of the cost of capital and cost of labor that you need to use in order to produce 1 unit of output. So you do your maximization problem, and then you find something that is fundamental for our analysis, which is this pricing equation.
So you don't
Yes.
really have capital here, right? It's just a drawing, and there is no real investment.
You don't have any investment. Yes, you have a TFP that is drawn when you enter, and then you have a technology that uses capital and labor with that TFP. You can think in terms of a Cobb-Douglas, for example, where you draw the A, and then based on your A, you decide how much labor, much capital to use.
Okay, then and what is the labor requirements you wrote here? It is derived by the...
So the labor requirement. No.
I see.
Yes.
It's to develop the different.
Yes. Yes. So yeah, I mean there is a unit input requirement which is priced omega, and then in order to develop you have to pay something else in terms of the sunk cost. So why this is something that we care of? Because it tells you that the price is, again, a combination of a standard CS pricing rule, that is a markup over the marginal cost, and this intercept part, with weights determined by the deltas. And so actually you can bring this to the data in a simple way, because we can do that for the export data, so the price of exports. In a given market, you can evaluate which is the Pmax there, and you can run a regression on the Pmax and all controls. And if you were in a CS demand system, this Pmax or any proxy of this Pmax should not matter at all, because everything is about the marginal cost and this constant elasticity. Instead, if this Pmax has a sign that is significantly different from 0, then, I mean, this is not going to be a CS. And this is something that we see. Why not having a CS may be important for what we want to do is because with the CS, you have a constant markup over marginal cost. So say you can measure this cost of these factor prices, then what you see is anyway that there is a constant pass-through and complete pass-through from the Ricardian item, which is this technological parameter, to the price. And then there would be, which means that when you want to back up this V from the data, you're going to say, okay, pass-through is complete, and that's one-to-one. What I observe in the price is going to reveal what I do not observe in this V. If there is instead incomplete pass-through, it's not that simple, because incomplete pass-through means, with this item in front, means that what I see in the data in terms of prices is not perfectly revealing this marginal cost here, or this technological parameter here. So I need an additional adjustment in order to back out what is V. So through this maximization, which is done product by product, then you will have a free entry condition that is considering the expected profits that you could make in your domestic market, which is this entire thing here, and the expected profit you may make on the foreign market. And the two together, due to free entry, will match the sunk cost of entry. Now, why are these expected profits? This is just the aggregation of the profits you would make across all the varieties. And here, this is the distribution of the Cs. So you are aggregating across all the different possibility of Cs. And so when a firm enters, we said it enters under the veil of ignorance. So the firm doesn't know how many products it's going to be able to sell. And it doesn't know even whether it will be able to sell at all. It will be able to sell a product only if its marginal cost of production is, well, here the unit input requirement is low enough with respect to some endogenous cutoff. Why there is an endogenous cutoff? Because we said that these demands, they cross the vertical axis. So at some point, if it is very costly for me to produce, I will not be able to price below this P max. And so if there is an upper bound for the price that is feasible, it means that there is going to be an upper bound for the marginal cost that is feasible, and this is what the CD is this upper bound for the unit input requirement in the domestic market. Then you're going to have a similar condition for the export market, but in the export market, you don't have to stay below your P max, but you have to stay below the P max of the foreign market, considering that in the foreign market, you have also to ship goods, so there is a iceberg trade friction, and also you have to consider that your factor prices may be different from those embedded in the foreign choke price. So the expectation has to take into account of these aspects, and you have these two. When you look at this and what we have seen before, essentially you realize that the only two things that are unknown variables in these expressions are the two cutoffs, because all the other things are expressions either of the cutoffs or of exogenous parameters. And so given that you have one of these expressions for the domestic country and one for the foreign country, you can solve for the cutoffs, because you know that the foreign cutoffs are going to be related to the domestic ones. So, but in order to do that, you need to make an assumption on the productivity distribution, or the unit input requirement distribution, which is the inverse of the TFP. And if you assume that TFP at the firm level is distributed as a Pareto, then C is going to be distributed as an inverse Pareto with this form, which is, well, C, of course, that's the variable, divided by Cm, which is the upper bound of the support, and the power of K. K is the shape parameter, and Cm is the location parameter of this Pareto, the upper bound of the support. Intuitively, the higher is the upper bound of the support, well, the higher the probability that you get bad draws for your unit input requirements, because clearly you are extending the support in the costly direction. And what the K does is instead, the larger is K, the more the distribution is skewed towards this upper bound of the support. So K, when K increases, it increases the concentration of the distribution towards the upper bound of the support. This Cm is our definition of the exogenous component of Ricardian comparative advantage, because this is what we keep as exogenous. So it's the industry characteristics. Then there is going to be an endogenous selection, and this endogenous selection will complicate, of course, the task of getting to the Cm. So variation in Cm in your country relative to Cm star in the foreign country captures Ricardian comparative advantage. Variation in the factor prices between the two countries, they capture Echelon comparative advantage. Now you can solve for these cutoffs. And why you want to solve for these cutoffs? Because they embed the Cm, which is the item we're after. So these are these are indeed the famous numbers by Ricardo. These are the Cms. Now we need to, of course, look at the open economy, because this is what we see in the data is an open economy. But we also have to have in mind what is the closed economy. Why? Because Ricardian comparative advantage is defined in terms of the autarkic economy. And this is the main challenge. So all these definitions of a comparative advantage, also in X-shareholding, they are referred to autarky. And so this part is unobservable. But as you see, some of the parameters that are in this unobservable part, they appear also in the other part. And so we will use the open economy to get to the closed economy in a sense. So intuitive, what this is showing is that, so CDAZ is the endogenous upper bound of the conditional distribution of unitary input requirements. That is the maximum unity input requirement that allows a firm to sell in this market. Firms that draw a unity input requirement above CDA in autarky are not going to be able to sell in the autarkic market. They are too inefficient. There's no way they can compete in this market, and so after entering, they exit. And those that are instead can stay below, they will be able to produce, and some of them will be able to produce several products if they are far away enough from this cutoff. And the cutoff depends on the Ricardian aspect, exogenous aspect. We may call this the state of technology. This is what, for example, Eaton and Kortum use as a term. So this is the state of technology for the domestic country in sector Z, the upper bound of this support. And then you see that intuitively, the lower is the upper bound of the support, the more selective is this industry, so the lower is CDA, because essentially you're going to have good firms that are competing. The larger is CM, well, the less selective is this industry, because on average, these firms are not that good. Then you have other parameters of interest. The larger is FE. This is the sunk cost of entry. So if you have high barriers to entry, then this is not going to be a very competitive industry, which is intuitive too. And then also what you have here is an index of product differentiation. We said that the gamma divided by alpha is an index of product differentiation. Alpha divided by gamma is the opposite, and this is going to affect also competition here. And so remember, we are now in a setup in which we said it's not only CS, but it's something else. And so delta has to be negative. And so what this says is that the more people perceive products as different, the weaker is selection, because clearly, if I say something that is different from my competitors, I can price a little bit more and they will buy it anyway. And the same for the foreign country. Then in the open economy, you can solve the model with the export market. And you see that there is one thing that is two things are going to be there on top. Of course, foreign variables. So how much is the gap between input prices between the two countries? The foreign Ricardian aspect, so the state of technology of the foreign country, and then the trade barriers. And then here you see the relative size. So this is the complication. If you want to back out the CM and this relative to CM star, which is this Ricardian numbers, then you have to net out of what you see in the data. You have to control for the relative factor prices, relative sizes, and the freeness of trade. So this row is tau to the power of minus k. Tau, we said, is a measure of the frictional iceberg cost. This is the inverse, and so this is a measure of trade freeness. So this is essentially representing the task. In these models, you can write all the endogenous observable variables in terms of cutoffs, but the cutoffs themselves have all these things inside. So Definition of comparative advantage, and there are a list of results, but I will go fast on those because they are just, well, I will give you the intuition, they're just theoretical results from the model. So home has a Ricardian comparative advantage in industry Z respect to industry Z prime, whenever compared with foreign. In that industry, its autarky average firm unit input requirement is relatively lower. So this is the Ricardian definition in terms of unit input requirements. I observe, well, I cannot observe, but say that if I add the unit input requirements in these industries, I would define, this is the way, the 4 numbers in Ricardo. Now, these are, what is one of the difference we said, is that, but there is selection here. So these are endogenous variables, these cutoffs. They are not the exogenous variables. Clearly, given this result, we see that if we take the ratio of these two things, a lot of factors disappear. And in the end, we get simply the ratio of Cm over Cm star to some power. And so we can say that home has Ricardian comparative advantage if the state of technology is relatively better in that sector. So this is the way you map the definition in terms of things that may be in autarky you can observe, which is after selection takes place. So the endogenous Ricardian aspect, it's linked anyway to the endogenous Ricardian aspect. What is the difference between the two is this k at the power of k plus 1. And so this is the incomplete pass-through I was talking about, because if you add CES, this ratio would be simply the ratio of the two without any exponent. But since it is not CES, you have k at the power of k plus 1, which is less than 1. And therefore, what you have is that the pass-through from CM to CA is incomplete, because if you take the percentage change to percentage change, you see that it is less than 1. Yes?
It would be incomplete also if you had CS, but you didn't have Pareto.
It would be incomplete if you didn't have Pareto.
Even with CS?
Yes. So, no, absolutely. So, if you have Pareto, here is coming from the demand. And it comes from the demand that is highlighting the role of firm heterogeneity here. Because K is a measure of firm heterogeneity. We said it is how much the distribution is skewed towards the upper bound. So it is the larger is K, the less heterogeneity you have. The smaller K, the larger heterogeneity you have. And so looking at this, what you can say is that the more heterogeneous firms are, so the smaller K is, the more incomplete the pass-through is. So, I mean, having a non-CS demand system with Pareto, it is introducing this, if instead demand is non-CS, is introducing a bias in backing out CM from CD.
However, you principally should have a distribution of sales that also reflects. It doesn't reflect the Pareto because you have different demand. So if you had CES and Pareto, the distribution of sales would also be Pareto.
Mm-hmm.
Now, because you have Pareto, but you don't have demand, you don't have CES demand, and I wonder the distribution of sales maybe it doesn't reflect Pareto. Maybe it does, I don't know.
So the distribution.
Something that you can compare with the data.
Yeah, I mean, it's something we can look at and characterize this distribution, yeah. Now, can we generate what we see in the data with this demand or with this model? So what is export propensity and what is export intensity? Export intensity, we said in a sector Z is just export divided by sales, so it's export, the fraction of exports on sales, or if you want, is the average export per sales across firms, while the export propensity is, in the model, is the fraction of firms that export which is an ex post definition. But since you have Pareto and a continuum of firms, due to the law of large number, it can be related to something that is ex ante, which is the probability that the firm exports. And so this is what is the export propensity. So home export propensity, I mean, here is chi, so this export propensity increases with Z if and only if home export intensity increases with Z. So, okay, I mean, this is mixed up. But, I mean, the message of this is that they go together. They move together. And so we don't have to consider the two panels, because if we can show that the model is hitting one of the two variables, then the other will be hit too. So first, Alice facts. Export propensity, export intensity. Now, the relation between the relation of chi with its, sorry.
Okay, that's actually very nice. However, then you can use one of the two, the one that you don't match with the data, to see if the model predicts it as you have.
Yes. No, and this is actually, I mean, it is, I mean, you're pointing at the key thing. This one is a macro variable. If you have industry data, you know what this is. This is a micro variable, which means that if the two are linked like this, then it must be that you can write, possibly if you're lucky enough, you can express one in terms of the other, which is actually what we can do. And this is why we can use the macro data. But as I was mentioning at the beginning, unless you have the model, you're not able to state that. Yes, exactly. Exactly. So this is a crucial result that is written in a mixed way, but the math below is correct. So, and then essentially, I mean, here without getting into much details, we can, by imposing some restrictions on the parameters of the model, we can hit the different facts. I don't want to waste too much of your time on this. And a crucial aspect is that with the CS, you will never be able to get to the facts of the CS and Pareto to the fact on the export mix, because in that case, in a CS setup, the distribution of sales across products is always the same. So it doesn't matter if you cut the Pareto distribution or not. So then, since this is a Ricardian setup, we now move to writing all the aggregate variables in terms of these fundamental variables, the cutoffs and export intensities, etc. So you want to know what is the open economy productivity at the industry level. You have to compute output per per input, and you can get, I mean, again, here I can move fast. The key thing is that this is just the definition, so you have here the TFPQ is output divided by your total cost of inputs. And then you can decompose this ratio of productivities in each industry between the domestic and the foreign country in three components that are some way telling you how the structure of the model works. You have an ex-ante component, which is the ratio of these average productivities in the two sectors at home and abroad in autarky. We've seen that already. This is just the inverse of the cutoffs in autarky, to some extent. Then you have two components. An ex-post amplifying component, ex-post meaning after trade. You're going to have a part that is amplifying and a part that is dampening. And you cannot tell in general which one dominates. So this is something that has to be asked to the data. The crucial thing is that these components can be written in terms of functions of the export propensity. And the fact that can be written in terms of the export propensity means already that you see some kind of a sufficient statistical result. You don't have to invert the entire model to see whether one component is larger than the other. If you add data on chi, on trade freeness, on the shape parameter, and on the relative size, you could already try to ask the data which one is dominating. So an important aspect of this is saying that when you go from the closed economy to the open economy, your comparative advantage may be amplified or may be reduced. And so that's why the revealed comparative advantage index is not going to work that well, because it's not going to take into account that what you observe may be amplifying or reducing the actual comparative advantage. I mean, you can also consider an unweighted measure, which is, what is the weighted measure? The weighted measure is telling you that you have to take, if you want to compute the average productivity of an industry, you have to consider that the number of firms or the share of firms that are very productive with respect to those that are not very productive. Why? Because those that are very productive are also bigger. And so it's like you need to weight them more. But it is interesting to look also at the unweighted one, because the unweighted one is not considering the type of reallocations that you may observe between firms. And in that case, if you consider that bigger firm, that more productive firms are bigger, then you only see the ex post amplifying component. Why is that interesting? It is literature related. The main paper on comparative advantage with firm heterogeneity is a paper by Bernard, Redding, and Schott, in which they do an X-share-only model, and they show that the X-share-only comparative advantage may be amplified by an endogenous Ricardian advantage due to selection. And the reason why they have that result is because their definition of productivity is unweighted. If they had instead used a weighted definition in their model, then they would have the additional component that we have seen before. So this is just an aside in order to connect to the literature. So now, we have 15 minutes, and so this is good enough to get into the quantification of the results. And so here, what are the challenges? Clearly, Ricardian comparative advantage is defined in autarky, so autarky information is seldom available. The paper I quoted at the beginning by Bernhofen and Brown is very interesting because they look at Japan. In an historical episode of trade liberalization, Japan went essentially really from autarky to free trade, forced to open up by colonial powers. And in that case, they can actually do this natural experiment of autarky and free trade. Observed productivity can be different from underlying productivity due to selection, as we said, and then there are the presence of the comparative advantage. How do you deal with that? There is the structural approach that is inverting models, but none of these models have endogenous selection. So our approach is really this sufficient statistics, and here is the list of sufficient statistics that you need. So the Pareto shape K, so this is with microdata. Microdata. The Pareto shape K, trade freeness rho, export propensity, export intensity are sufficient statistics for the ex-post amplifying and dampening components of relative TFP. The sufficient statistics for example component further include the relative prices. And so this is the ex ante component, where you see that you can get to this thing using the sufficient statistics, because this ratio itself can be expressed as a ratio of factor prices and then these combinations of export intensity. Yes?
How do you make comparisons across
two industries?
So, of course, you have, so say that this is what we're after, this is for the same industry. You can compute it for all the industries in your data, and then you can rank them according to these ratios. And so you will have that, you can say that when this ratio is very high, we have a comparative advantage. When it is very low, we have a comparative disadvantage. And so you have a continuum, a ranking of all these sectors in terms of sectors that are that have stronger comparative advantage. So that's yes, you have to, I will show some pictures of those. Now, clearly this is based on firm level data because this chi is a micro variable. This is the share of firms that exports. You need to have this information. But as we were discussing before, after Federico's question, there is a way through which you can write chi as a function of theta, and theta is a macro variable. And so in that case, you can rewrite with macro data this type of relation as something that has only macro variables. In this case, you have the relative markets, relative number of consumers in the two markets. So you can also write the Balassa index in the model. Balassa index is by definition is the measure of specialization in exports across sectors with respect to the rest of the world. And this is the main component of the index. You can also evaluate with sufficient statistics this component of the Balassa's RCA. And I mean, one could check whether this Balassa RCA is the one that you would get looking straight at this type of things. So when you do that, the ranking of industry based on Balassa's RCA is the same as the ranking based on export propensity and intensity, or to this item here that is a combination of Echelon and the Ricardian comparative advantage. So why is that something that may be interesting to look at? Because we can do some counterfactual analysis using this term here, while keeping all the rest as given. So we may change factor prices and see what happens. So China is getting higher, increasingly higher wages, and so it's becoming more costly for labor. So this may affect their relatively factor cost. And then we can look at what is happening in the economy and how the specialization is changing, etc. What kind of counterfactual is this? One may say, okay, but now you're doing counterfactual in which you change an endogenous variable, which is not much of a counterfactual because everything should change. So the idea here is that you're changing relative factor endowments in order to get this type of result. So the comparative statics there is on the relative factor endowments. So quantification, first thing, the test of VS and CS. So this demand system has been used in development recently again, I mean, 2015, but the paper is still under review at Econometrica. So you can estimate this type of equations without, so this is what they do, but let's focus on what we do, which is something similar. So here you have firm end price for product K in market J as a function of the choke price there in that sector, in the market of destination, then a long list of firm, market, and industry controls. And so essentially, if you had a CS system, this thing here should not matter. One may say, okay, but P max is the maximum price you observe there, could be an outlier, and so it's not, I mean, there's a lot of noise there. Now, noise would play against us. But if you wanted to put something different, this P max can be expressed also in terms of the average price or any moments of the prices under the Pareto assumption. And so when you test this, you find that indeed this phi is not 0, it's significantly different from 0. the phi in,
principle, you would like,
yes,
in principle, you would like to have the choke price there.
sorry?
In principle, you would like to have the choke price there.
Yes, which is this one.
This one focuses on
Yeah,
the choke price.
yes. And the phi, according to the model, is just a transformation of the delta. If you remember, the pricing equation was this times the Pmax plus the markup over marginal cost. So we get this estimate, and okay, I mean, we have all these estimations, but the main result is that not only we need to assume that it's non-CS in order to get the intra-Fermi allocations across products, but also there seems to be some direct evidence that maybe it's interesting to not to have CS, and it is relevant for us because of the incomplete pass-through that we discussed. Now, using micro and using macro data, we have 5 minutes, right? So here where we get the parameters, the shape parameter, log and log regressions on the CDF, on the cumulative density function of firm TFP, something standard. The rho, the index of freeness, again, something standard. There is a method by Head and Rees to obtain the rho from trade flows and domestic absorption. And then for the sake of argument, for the application, we use this simple Cobb-Douglas production function. That means that the relative unit input prices are just a weighted average of the relative prices of the two inputs, index Z, which is the industry index. We can do better than this, I think, but this is what we do for the moment. Relative income is GDP per capita, and so these are the parameters that we use. And using these parameters, we get all the different things that the components of the that we were discussing before. So what we have is that the ex post relative inverse average unit input requirement rises with export propensity. So this is the amplifying component. But when you consider both the amplifying and dampening component, you have a fall. So the dampening component dominates. So this is the ex post component of relative inverse unit input requirements, so the average productivity. Ex post component of average productivity. If this is upward sloping, when larger than 1, you see export propensity as a function of export propensity. This is amplifying, and this instead dampening. The export propensity falls with relative prices, which is something that hopefully is built in the model and it is there in the data. The export propensity rises with your own productivity, so with the unit input requirements exogenous part of the foreign country. And so here you see from export propensity, we're able to back out the relative, the exogenous, I mean the magic numbers in Ricardo. So we have export propensity, we have all the other variables that we have calibrated. With those simple expressions for each industry, we're able to get out what is the corresponding CM over C. So C max, but this is CM, the CM that we've seen in the model. This one. And then, I mean, export selection extensively reshaped Ricardian comparative advantage. So we have relative inverse average inverse UER, again here. These measures of unweighted and weighted TFP. And what you see is that export propensity is the selection part of the story, because if we didn't have selection, then all firms would export or would not export. So, I mean, this is really showing you how the selection is important for the analysis. And then we can evaluate the relative productivity gains from trade. We can look at various correlations here. But then we can also look at the erosion of comparative advantage, and this is the last thing I want to show, of China's extraordinary comparative advantage. Rising labor cost in China erodes its comparative advantage. There is already a literature on this. Which industries would be revealed as China's comparative advantage in the Ricardian sense, and disadvantaged industries when factor prices evolve? This question can only be answered by counterfactual simulations. You have to solve and fully estimate the general equilibrium models, but with sufficient statistics, you can say something without having to solve everything. And the something is captured in this table and the next picture. So what do we have here? So the experiment is that we've calibrated the model in 2004. Now we change the relative factor endowments so that they are such that the relative unit input prices are those that we observe in 2019. And so here the baseline is 2004, and 2019 is the baseline, is the counterfactual analysis. Why is that counterfactual? Because we're keeping the technology the same as 2004, while clearly in 2019, China may have had a very different technology, at least in some sectors. So that's why it is counterfactual. Here you have the list of top 10 industries, bottom 10 industries. Here you have the churning in the rankings. The number in red is what it was in 2004, and now it is affected in with this counterfactual in 2019. And so you see there is a churning. Coming back to your question, this is the ranking of sectors that we were talking about, and this, you see that the churning of sectors. You can look at the churning along the entire distribution. And so baseline ranking 2004, the new ranking here, the 45-degree line would be no change in ranking. And you see there is action, and there is a lot of action at the bottom and the top of the distribution. If you zoom in the bottom distribution, you see something interesting here. That is, you have the 45-degree line, factor price equalization in green. You have in red factor prices in 2019 with K equal to 10 times what we have in the standard counterfactual. And so the red line has less heterogeneity than the one that we used for the table. And so you see that indeed the degree of heterogeneity of firms is going to affect how the ranking is changing. So from this picture, what we bring home is the fact that, well, you can generate this type of counterfactual analysis, but also that firm heterogeneity is quite important for the picture that you show. Okay, so macro data, you can do similar stuff, but now it is across all countries. You can therefore redo the analysis with the average export intensity across industries and TFP gains from trade, and then you can figure out which countries are gaining the most from trade with respect to autarky, which is not what you observe. And typically, the small countries are benefiting more than the large countries. What is interesting in terms of what you were mentioning before, Federico, is that the numbers that we get from China from the macro data are in the same ballpark as those in the micro data, so there could be some kind of possible validation. So I will conclude here. This is just summarizing what we've done, but I hope I have some way conveyed the main message of this project, which is to find a data non-intensive way, or mathematically non-intensive, computational non-intensive way to revisit the concept of revealed comparative advantage and offer some kind of handy way of measuring it, even in setups that have all these complications based on the recent literature. Okay, thank you.